So in this lesson, we're going to look at the change of state and what that means in terms of the energy of particles. Now, the first thing we're going to do is we're going to look at the changes of state in terms of internal energy. Then we're going to look at something called a cooling curve when a change of state is happening and be able to identify from the shape of the curve when the change of state is happening. And we're also going to be able to calculate energy for state changes using something called a constant of latent heat, either for vaporization or for melting, right? So we're going to do some defining, some identifying, and some calculations. Now, you've probably covered the different states of matter in a lot of detail. And just to remind you that we have solids, liquids, gases. I'll briefly mention something called plasma. But the difference between the solid, liquid, and gaseous state is specific to the energy of the particles. As we go from a solid to a gas, the kinetic energy of the particles increases, and so does the mean separation. The changes are very important. You need to be able to identify the names of the changes. And so from solid to liquid, we have melting. From liquid to gas, we have vaporization. From gas to liquid, we have condensation. And then from liquid to solid, we have freezing. Right? So those names are important. There's also sublimation, but we don't really talk about that in physics. And the last thing I'll mention is plasma. Now, plasma is sometimes referred to as the fourth state of matter. But basically, it's what happens when you get a gas, which you superheat. And we're talking about the outer layers of the sun. So it's not something we come across very often. But basically, when particles gain even more kinetic energy, then eventually electrons are ripped away from them. And you have a highly ionized gas. So it's just quite nice to visualize that. What happens when even gases or gases with a lot of energy have even more heat energy applied? You would eventually form this weird plasma state, but we don't talk about it very much. We do talk about evaporation, and I'm going to mention this because there are two changes of state associated with liquid to gas, right? One is called boiling, which happens at 100 degrees Celsius, and is basically only going to happen at that temperature. But then you have evaporation. Now, evaporation happens, depending on the environmental conditions, a wide range of temperatures. So you can see here, this is a nice illustration of a water droplet evaporating. So why does it happen? Why isn't it at 100 degrees? Well, 100 degrees is when all the water starts to change state because it's receiving energy entirely. But what happens when water evaporates is that the change of state happens only on the surface. Basically, the surface particles have higher energy and so break away, and very few particles actually receive enough energy to escape this liquid lattice. The energy is transferred to them from the particles of the surrounding gas. So in this case, you've got air, and particles in air have a lot more kinetic energy than the particles in the liquid. And so these particles here are bombarding the liquid droplet, and they are passing on their kinetic energy to the liquid particles. So the ones on the top of the surface eventually go up an energy level, they increase their energy, and then they can escape. Right? So that's the basic idea, or the basic difference between boiling and evaporation. Boiling only happens at boiling point, whereas evaporation happens on a range of different and a range of different temperatures, and only on the surface. So let's have a look at what happens when a material changes state. Now here we have a cooling curve or a heating curve. In this case it would be heating. And we're taking a material, let's start with a solid, and we're increasing its temperature. Now this range here would be simply what we come across when we're trying to find the specific heat capacity of a material. So the experiment that we did the other day, where you're increasing the temperature of an aluminium block, you would have seen that you are increasing its energy input, its Q value, and its temperature is increasing, right? But what if you kept adding heat so that it melted? And then if it was a liquid, right, you would heat it, it would get hot. What would happen if you increased its temperature until it became a gas? Well, interestingly enough, this is what happens. The temperature energy input graph goes flat where that change of state happens. Right, so let me tell you why. Now, we mentioned internal energy at the start of this topic, and we defined it in terms of the kinetic and the potential. So what we're going to do is we're going to look at that heating graph, thinking about what's happening to the particles. Because as temperature changes, if you remember, temperature is directly relevant to kinetic energy. So where you're seeing a temperature increase, like there, and there, and there, you're seeing a change in the amount of kinetic energy. And where the temperature is not affected, then heat is still coming in, but what's going on there, or what's happening on there, is the intermolecular forces are broken, and that needs potential energy. So what you're getting there is a change in potential energy. So let's break this down step by step. Here we've got some chocolate melting there. So say we've got a solid and we are heating it up. That means the heat is coming in. If you add heat and you give particles of the solid more kinetic energy, they vibrate more, and so the chocolate just gets hot, right? And its temperature increases because its kinetic energy is increasing. And so that's what's happening here, and the particles pretty much just vibrate, right? They vibrate fixed around a point. But when the chocolate starts to melt, heat is still coming in, right? So heat is still being added. But this time, there is no increase in kinetic energy. The extra energy that's coming in is breaking the bonds. And this is increasing the potential energy of the particles, right? So they become free. That energy is almost like a payment to try and break the bonds. And then that would register as an increase of potential energy. Now, because no increase in kinetic energy is taking place, there is no increase in temperature. Okay. Now, the liquid then, once all those initial bonds are broken, they don't need any more potential energy. They don't need to break any more bonds. So what happens now is as you add heat, the water just gets hot. The heat raises the kinetic energy of the particles vibrate more, and so the temperature increases. And then it all happens again when we get to that boiling point, right? When the boiling point starts, then those bonds which are keeping the particles in a liquid formation start to be broken. That's an increase in potential energy, right? Not an increase in kinetic energy. And so therefore the temperature does not change. And all the heat energy is being transferred to potential energy. And then what you're getting is a gas formed, and then you can continue heating that gas up, and the particles will vibrate more and more and more, and as they're vibrating more, there's more kinetic energy, and you get an increase in temperature. So hopefully that makes sense now. Kinetic energy relates to an increase in temperature. Potential energy relates to no increase in temperature and a breaking of the bonds. Now, what happens when something's cooling down? Because that might be a little bit harder to try and imagine. Now, if this gas was to cool down, you can imagine like it losing energy. So the energy is coming out, Q's coming out here, and it's starting to cool down. Well, you can understand why this vibration would start to drop and the temperature will start to go down, right? But then what happens when the bonds start to form? Well, basically, the temperature doesn't change, because instead of throwing that energy out, it uses the energy, it holds on to that energy to make the bonds again, right? So you're not registering an energy change, but you are still using the energy. So the energy is still coming out of the vibration, but it's going into bringing the bonds together. And then the same here, as it cools down, then the particles are losing energy. Kinetic energy is becoming heat energy, is coming out. But then as the solid and liquid phase begins, as it solidifies, then that Q, it doesn't throw it out, it uses it to build bonds again, and then the temperature stays constant, right? Because there's no kinetic energy change. It's just the Q is being used to build bonds, and then you end up with that solid formation where it can begin to cool down again. I hope that made sense. All right, so now the maths bit. Now, obviously, depending on the material, because obviously the bonds, when we're talking about the van der Waals forces, we're not talking about the chemical bonds, we're talking about some intermolecular bonding, and that really pretty much depends on the properties of the material. And so every material has its own specific latent heat of a substance, right? So it's the amount of energy transferred when 1 kilogram of a substance changes state at a constant temperature. And so you have a specific latent heat of vaporization. So that's the amount of energy that a substance needs to become liquid to gas or gas to liquid. And the specific latent heat of melting, which is the amount of energy that a substance needs to become a liquid if it's a solid, or to freeze if it's a liquid, right? So every material has two different specific latent heats. Okay, and this is how the maths would work. Your specific latent heat is the amount of energy transferred during that change of state divided by its mass, or Q, heat energy, equals mL. And I would like to add that the specific latent heat of melting, which is this one here, is usually less, I think it's always less than the specific latent heat of vaporization. Because to break the bonds from here to here, the energy needed is actually less than to take a liquid and become a gas. So this value is always greater than this one. So please ignore the fact that it doesn't show that in this graph. This graph is a bit nonsense, but this one's much better. So you can see here a bigger difference because the amount of energy required to break bonds is much greater. Okay, so let's see if you get this now. We have the latent heat of vaporization of water, that's the amount of energy needed to go from a liquid to a gas, and ethanol are 2.27 times 10 to the 6 joules per kilogram and 8.55 times 10 to the 5 joules per kilogram. Which one is easier to turn into a gas? And how much thermal energy is needed to turn 50 grams of ethanol into a gas at a boiling point of 78.3 degrees. Try it now. Switch off the video and have a go. See if you can use the equation. I hope you've tried it before you're checking the answer. No cheating. And so you should be able to see that it's easier to boil ethanol because much less energy is needed. You can see there's 2.27 times 10 to the 6 versus 8.55 times 10 to the 5, which is much less. And if we calculate the amount of energy, you should have gotten 4.3 times 10 to the 4 joules. This is pretty much it. There shouldn't be many challenging questions. It gets harder once we put this equation together with the specific heat capacity equation.